observation here. All right? And so, in fact, it turns out that there are these two ways in which the tectonic deformation can be accommodated across plate boundaries and across faults. One is earthquakes, and the other is what's called creep. Okay? So some plate boundaries are what we call locked. Okay, so they are completely locked, they are completely stationary. That's what I've been showing you in those little cartoons about the earthquake cycle. And so they just deform, they bend until they break, and you get an earthquake. And in that sense, all of the plate motion is accommodated by earthquakes, by slip on the fault. Sudden instantaneous earthquake slip on the fault. But some faults also exhibit what we call creeping behavior. And this is the behavior where these faults are sliding past one another very slowly. So I'm getting ahead of my slide. So this is what we've been talking about up until now, where this is showing a locked section, and it builds up, the strain builds up, you get this S shape. The strength of this fault is no longer sufficient to withstand the strain, and it pops, and you get an earthquake. And then the other type of deformation, the other end member, is that all of the plate tectonic motion is being accommodated by continual gradual slip along the fault. So these two faults, these two blocks, are just gradually sliding past one another without any earthquakes. Ideal, right? No earthquakes, no hazard. Well, there's hazard if your house is built on the fault, but less hazard if there's no earthquakes. Okay, no sudden shaking kind of motion. So, we're talking about the Hayward fault. We can look a little bit closer to home. It turns out that the fault is creeping through Berkeley as well. Okay? And so very famously, there was this section of the stadium. This is actually a photograph standing down on this side of the stadium, on the south side of the stadium, looking up the wall, and there's this offset. Now, I told you that they rebuilt the stadium, obviously, and I told you that they left the exterior wall. Well, I'm not quite sure why, but the exterior wall still has this offset. So this offset, the fact that this section of the stadium is misaligned with this section of the stadium, is due to the continual creep on the Hayward fault. So because the fault continues to move and the stadium was right on top of it, we were deforming the stadium. Okay? And this is largely why the stadium had to be rebuilt, because of deformation in the internal structure of the stadium. Yeah. The question was, so locked faults can creep too, i.e. you have some sort of... so I'll answer that in a minute. Okay. Any other questions? Okay, so in the stadium we do see a creep, and it turns out that we see creep on several of the faults through the Bay Area. Okay, we see creep on the Hayward fault, we see creep on the Calaveras fault, and we see some creep on the San Andreas fault further to the south. The lines in red here are locked sections of the fault. So they are completely locked. We see no evidence of creep, meaning that all of the motion that needs to be accommodated across this section of the San Andreas fault can only be accommodated in earthquakes. Okay, so green is good. We're accommodating some of the deformation without earthquakes. So now we know, how do we figure this out? How do we figure out which are creeping and which are locked? Well, we have to go and collect as much data as we can about the deformation. One way is to go and look for offset structures. Obviously, here's a fence that has been offset. This is on the southern section of the San Andreas fault. Okay? This has been offset, and there's been no earthquakes during a period when there were no earthquakes on this section of the fault. This is the central San Andreas fault further to the south. This is the Calaveras fault in Hollister. Hollister is quite remarkable. If you go to Hollister, you can track the Calaveras fault, and you go from sidewalk to sidewalk, and you see offsets like this, a huge amount of creep down on the Calaveras fault. It's quite remarkable. Hollister also, I think actually they've closed down now. They used to have a brewery called the San Andreas Brewery, which was also right on the fault. That was very good. Okay, so we have these two types of behavior, the creeping behavior and then the locked faults. So the creeping behavior is aseismic, meaning if a fault is 100% creeping, then there are no earthquakes. That's why we say it's aseismic, whereas a locked fault is 100% seismic, as in all of the deformation is accommodated by earthquakes. Okay? So aseismic, creeping faults, the blocks are constantly moving, and so there's this free sliding of the two blocks next to one another, when a seismic section is where we have earthquakes and what we call stick-slip behavior. Right? These two sides of the fault are stuck together, and then they slip, and they stuck, and they slip, and they stuck, and they slip. Okay? And so as it says in the title of the slide, but we have this spectrum of behavior. It's not that a fault is entirely aseismic or entirely locked. Of course, you can have behavior that's in between, where you do have some creep, but you also have earthquakes. Okay, so you can get a combination of the two. And Roland's group likes to think of this. You saw I didn't point it out, but you saw the hair but they like to use the hair for the locked section, the tortoise for the creeping section, and somehow they decided this is an alligator. I don't quite understand that. But anyway, so this is a combination of locked and creeping. Okay, and the way that this works is that there can be a locked patch. So in this case, this section of the fault is locked. Okay, and so there's what they call a locked disparity. There's some kind of particularly angular piece, for example, that has very high friction associated with it, and so it doesn't move, and so it stays locked, while the fault above it and below it and to the sides of it can be creeping. So that's when you get this combination of locked and creeping types of faults. Okay, and so that's exactly what is going on the Hayward fault. So back to our curve. So we know what the long-term build-up on the fault is. This is for the Hayward fault specifically, 10 millimeters per year. In this particular location in Hayward, the steady sliding, this offset of this curve, corresponds to about 2.5 millimeters per year. Okay, so you take your long-term rate, which includes everything at 10 millimeters per year, you subtract your 2.5 millimeters per year, and what you're left with, 7.5 millimeters per year, is the amount of build-up that is going to have to be accommodated in a future earthquake. Okay? So you sort of take the earthquake piece, you add to it the creep, and that gives you the total long-term rate. So the more creep, the better. 100% creep means no earthquakes. 50% creep means only half as many earthquakes. Okay? 0% creep means everything has to be accommodated in earthquakes. Okay? So the other thing to notice is that what we see at the surface is different. So for the locked section, as I keep saying, you have this S shape of deformation. So these are the current plate rates. So if you just watch what's going on at the surface, you can see that there's this deformation, this S shape of the deformation at the surface when the fault is locked. If you have creep, then you would have no motion here, and all of the motion would be on one side. There's no gradual change in the motion from one side to the other side of the fault. And then if you have both, of course, you have some sort of combination of these two. Okay? So we can go out and we can look for that deformation. So now we can do this because plate's moving relatively fast, 5 centimeters per year. We can look for the deformation that's building up due to plate tectonic motions, and we can look for that shape across the faults. And that tells us about whether a fault is locked or whether a fault is creeping, okay? In addition to going and doing things like looking at curves. And so we do that using a very high-precision GPS. This is the same GPS that everybody now has in their smartphones. But using some specialized equipment, these fancy antennas, and processing data over long periods of time, we can get accuracy down to millimeters. Okay? So we can see motion of a point at the surface of the Earth at several millimeters over the course of a year or two. Right, it's a very accurate GPS. So what you do is you go, there are these what are called benchmarks. There are these marks that are cemented in various places, including in this monument in Richmond. You set up your GPS antenna directly over this monument, you record its exact location, you come back a year later, you do the same thing, and you see how much it's moved. Okay, so this is the benchmark. You line it up, and so in 1998 you get this very precise location. If you remember when you were putting in the location of where you lived, you probably put in 2, 3, maybe 4 decimal places for the latitude and longitude. Here we're measuring out to 1, 2, 3, 4, 5, 6, 7, 8 decimal places. So that's sub-millimeter accuracy. Okay? You come back a few years later, in this case in 2004, and you get a very accurate location again, and it turns out that it's moved. You can see the amount it's moved is just in these last 2 digits. Okay? And that corresponds to a little more than a centimeter. So this is how much it's moved relative to the base plate. This little plate here is kind of about this size. I guess you can see down here. But so this little plate here, well, there's a scale. What am I doing? There's a scale. So you can see that it's a little more than a centimeter. Okay? So you go back, and that's what Roland's group does, is they go back to these benchmarks every few years, and they measure the location. And over time, you can see that the location has moved. So this is at the same location. It's moved, it's gone up north. It's moving in the north direction. And then this is the displacement in the east. It's gone down. That means it's moved west. So what that says is that this point is moving northwest. Right? We know what the strike of the Hayward fault looks like this, and so we can tell which direction it's moving. And it's obviously on the right-hand, it's obviously on the left-hand side of the fault, on the western side of the fault, because this point is moving to the northwest. Okay? So we can measure the rates at these various locations. They go out and they do these surveys all over the place, all throughout the Bay Area to sort of map the total amount of displacement, including in Memorial Stadium. And so they did this in Memorial Stadium. Here's one of the receivers on one corner of Memorial Stadium. But they did it on 4 locations around Memorial Stadium. And this is what they've determined. So what they've done is they've measured the deformation of these 2 stations, well, of these 3 stations, with respect to this station. Okay? So if you think about this point being fixed, this point has moved this much, and this point has moved this much. There's an arrow here, so this arrow is 10 millimeters per year. So you can see that this is less, about half of that. So in fact, the GPS-based creep rate across the stadium, across this section of the Hayward fault, is 4 millimeters per year. So the long-term rate, remember we measured Strawberry Creek has moved 335 meters in 32,000 years, and that tells us that the long-term rate here is 10 millimeters per year. We now know that it's creeping at 4 millimeters per year. So how much is left for earthquakes? 6 millimeters per year. Very straightforward. Okay? So every year we accumulate an additional 6 millimeters of built-up strain on the fault. Okay? So they go and do this all over the Bay Area, and this is a map that shows what the deformation looks like. And so all of these points are motion with respect to this point Lutz. So all of these things are done relatively. So you have to say, okay, this point, I'm going to assume this point is fixed, and I'm going to plot what all of the other locations are doing with respect to this point. Okay? So they've chosen a point that's in the middle of the swath of faults here. So this is north. It's on its side. I hope you recognize where we are, San Francisco, Berkeley. Okay? And so this is the Hayward fault that we've been talking about, and all of these observations here are the observations on Memorial Stadium. Okay? And so when we look at this, we can see evidence for both locked and creeping sections of the fault. So up here to the north, we see evidence for locked sections of the fault, both the Rogers Creek fault and the Hayward fault. And we can tell this is locked because there's this gradual change from rapid motion to the left in this diagram on this side to rapid motion to the right on this side, and there's a gradual change as we go across the fault. So that's because these faults are locked. We're deforming the 2 sides, the 2 plates, and the strain is being accommodated smoothly in between the 2. Okay? Down here is where we see a clear creeping section. Okay? If you look at these 2 points, this point is just on the western side of the fault, and this point is just on the eastern side of the fault, and you can see the entire plate deformation. Okay, so this arrow here is basically the same size as this arrow, and this arrow here is almost the same size as these arrows. So almost the entire plate deformation is being accommodated across this fault on an annual basis. So that fault is rapidly creeping, and we don't expect to have big damaging earthquakes on that fault. That's the Southern Calaveras fault. All right, is everybody with me? Any questions? And then the last piece here is that there are then sections of the fault that show both. If we look here at our section of the Hayward fault, you can see that there is a step function change. These are very small vectors, and then we get a sudden increase in vectors as you go across the fault. So that tells you that there's creep because there's a sudden change as you go across the fault. However, the difference between this and this is not the full plate rate. So we're not accommodating all of the built-up strain, and there's still going to be earthquakes. All right? No questions? All right. Okay. So now that the group has gone out and mapped all of these deformation rates, first of all, we can identify which faults are creeping, which are locked, and which are somewhere in between the 2. And then we can also develop models that explain, or that we map out what we think the built-up strain is on the various faults. So as we go fault by fault, we can determine whether we think they're entirely locked, entirely creeping, or whether there's something in between. And so this is what that looks like for our section of the Hayward fault. Okay, so this is now looking sideways on at the Hayward fault. So this is the surface, and this is depth, 10 kilometers depth. And the color scale here shows the degree that it's locked or creeping. So how quickly is a particular patch on the fault moving? Okay, so we have no data up here to the north because of San Pablo Bay. It's beneath the bay, so we can't get any data, so we don't know what's going on. Okay. Here in Berkeley, you can see that these yellow colors are getting up to the creeping end. So in Berkeley, we have sort of higher creep going on, although at greater depth, there seems to be a locked section. The white is locked. Okay. And then as we go further to the south, beneath Oakland, it's more locked than it is beneath Berkeley. And in particular, there's this big patch, this locked patch, deeper in the fault. Okay. And so there's this combination as you go along the Hayward fault. Different parts of the fault, there's more creep and less creep. The places where there's least creep are the most hazardous places because we're building up strain, which has to be accommodated in earthquakes more rapidly. The places where there's most creep are the best places to be. Yeah. So the question is, how can you differentiate between the creep rate at the surface and the creep at depth? And this is where the modeling piece comes in. So of course, we focused on talking about offset curves. That's telling you very specifically about what's going on at the surface. But then when you go and make GPS observations over some area, so that's what this map is about, once you have GPS observations over some area, you actually have constraints on how much creep there is at depth. Because if you have creep going on at 10 kilometers depth, it's going to affect GPS receivers that are some distance away from the fault. But if you only have creep right at the top of the fault, the surface of the fault, it will only affect GPS stations close to the fault. So by having a map view of what the deformation looks like, we actually have constraints at depth as well as at the surface. Great question. Okay, so you know, the message here is that plate tectonics continues to move at a fixed rate. When there is no creep on the Hayward fault, we have the long-term rate of 10 millimeters per year. We have no creep. And so if you take, I guess I did this in 2009, I should update it. If you go back to the 1868 earthquake, we've had 1.4 meters of built-up strain since the 1868 earthquake. So this would be relevant for this sort of southern section of the fault where we have the 1868 earthquake and there's very little creep. There's about 1.4 millimeters of built-up strain. If you have some creep, 2.5 millimeters per year, this obviously number goes down, so you're down to 1.1 millimeters of built-up strain. If you have more creep, it gets smaller. So the more creep you have, the better. So where you want to be located, and when you look at this fault, so this might explain why we have not had a big earthquake beneath Berkeley for 300 years, whereas we have down here because we're accommodating some of the built-up creep, some of the built-up strain with the creep in the northern part of the Hayward fault, but we're not doing it in the southern part of the Hayward fault. Okay, I'm going to stop there. Oh, one question, yeah. Okay, this is a great question. This is important. The question was, is there something that can be done to the white area so that it's not locked? I.e., is there some way that we could facilitate creep on the fault so that we wouldn't have an earthquake? So there is actually a movie about this, a James Bond movie about this, A View to a Kill, appropriately named, because of course as soon as you start to mess around with a fault like this, you may actually trigger an earthquake. So the short answer is no, there is nothing that we can do. We'll talk about that more a little bit later in the class. All right, don't forget to be signed up. Don't forget to be on time for the field trip.